It's very important for us to understand how inverses work before we can begin our study of logarithms. Our first definition is that of a one-to-one function. A function is one-to-one if it passes both a vertical and a horizontal line test. And if a function is one-to-one, then it is said to be invertible. Basically, which means it has an inverse, which is also going to be a function. Anytime we want to find the inverse of a function from its equation, we're going to first switch the x and y and then solve for the new y. Now, if we want to find the inverse of a function from its graph, we're going to reflect the graph across the line y equals x. In other words, if a comma b is on f of x, then b comma a will be on the inverse. In this first example, we're asked to find the inverse of this graph. Notice how this graph goes through 0, 4. Well, that tells me that 4 comma 0 will be on the inverse, switching a comma b to b comma a. If the x-intercept is at negative 2 comma 0 right here, we're going to have a y-intercept over on the right of 0 comma negative 2. Each x comma y becomes a y comma x. And I can draw in this inverse here. Probably should have drawn a little straighter of a line as such. And it turns out that anytime I graph a function and its inverse, they will be mirror images across this diagonal line y equals x. Let's do this with another problem. I can see that this graph has the point negative 3 and negative 3 on it in the bottom left corner. Well, if we switch negative 3 and negative 3 around, you still have negative 3, negative 3. So this point is actually on the inverse graph also. This has an x-intercept of just about negative 1.2, so the other graph will have a y-intercept about negative 0.2. We have a graph here of about 0, 1.5. The other graph will go through 1.5, 0. I see that this graph goes through 3, 3, so I think 3, 3 switched will be 3, 3 again, and I can pretty much guess that this inverse graph is going to look like that. Notice again how I can draw this diagonal line y equals x through this, and it will be a reflection on either side. Now, notice that this new graph here is not a function, because it fails the vertical line test. Well, notice how the first graph passed the vertical line test, meaning that the new graph will pass the horizontal line test, but the original fails the horizontal line test, meaning the inverse will fail the vertical line test. Since this first solid line graph given to us does not pass the horizontal line test, then it is not a one-to-one function. It needs to pass both the vertical and the horizontal line test to be considered to be a one-to-one function. For this next problem, they want us to find the inverse, and we've got the equation. So I'm going to rewrite this as y equals 3x minus 2. And our first step is to switch the x and the y. Rewrite this as x equals 3y minus 2. Then I want to solve for the new y, which means I want to add 2 to both sides of the equation, giving me x plus 2 is equal to 3y. And then dividing each side by 3, I can isolate the y by itself, and we can have x plus 2 all over 3. I think you will be more comfortable writing this as y equals 1/3 x plus 2/3 so that you can see it in slope-intercept form. Now, the original function g of x has a y-intercept of negative 2 and a slope of 3. So let's plot that. Y-intercept of negative 2, rise 3 and run 1 to get to our next point. And this will be the graph of g of x. Probably should put arrows on both ends. Now, this new graph has a y-intercept of 2/3 and will rise 1 and run 3 to get to this next point, and we can identify its line by crossing it through those two, and this will be the graph of its inverse. Since its inverse is also a function, we can actually give it the title g inverse of x. I know it looks like a negative first power, and that's what it is, but it has nothing to do with negative exponents. It's just the notation that we use here to represent the inverse of a function that is also a function. For this next problem, we have y equals x squared plus 2. If I want to find the inverse, I need to switch the x and y and rewrite this now as x equals y squared plus 2. And then solve for this new y value, which means subtract 2 on each side of the equation, and then square root each side, which gives me plus or minus the square root of x minus 2. Well, let's take a look at the graphs. The first one is a parabola that's up 2 units from the origin. So here we go. 2 units above the origin. It's got standard curvature, so I can go over 1, up 1, and over 2 and up 4 to get to 2 additional points. And notice how this passes the vertical line test. It really is a function, but it does not pass the horizontal line test, so it's not one-to-one. Now, when I go to graph the inverse is going to be a reflection across this diagonal line, y equals x. And if I change this 0, 2 to 2, 0, and switch 1, 3 to 3, 1, etc., we end up getting this graph, which I'm dotting in here at the right. Notice I do have mirror images, but this is not a function. Okay, if we actually look at the equation here, we've got a plus or minus in this equation. The plus, the square root, is the top half of the graph, and the minus is the bottom half of the graph. So it's not a function, and we use the word relation here instead. There is a relationship between x and y, but it's not a unique y for each x, and therefore it cannot be a function. And back up here at our equation, we cannot call this h inverse of x. This notation right here is reserved for functions. It cannot be used in this case.